Lecture 4, Part 4. This is about to identify the vapor quantity in the atmospheric column. Okay. We use the combine three basic equations from ideal gas law, hydrostatic pressure law, and the change of temperature with the height or with the altitude. We just combine these equations together. This alpha is mean the Laplace, the change of temperature with the elevation. The next we substitute low A in the from equation 4.4 in 4.5, and the next we substitute dz in the same equation, and we do integration from z1 to z2, and we got this relationship P1 and P2 and P1 is a function of the temperature and the power of G divided by alpha A. And the other equation we got, so this equation similar to this. Is a power function to explain the change of the temperature with the height, with the elevation, and the equation is the temperature with the elevation is a linear function. Okay. So the next we can estimate the precipitable water using this equation. The mass of air in this area okay, that is the mass in this area. If you go to area times dz and times the density of the air, and for the mass of water times the QV, because we know that just remind that QV is the ratio of mass of vapor okay. So when we time with the mass of air, so we got the mass of vapor, mass of water convert from vapor. And finally we got the total mass of water in the column is integration, and we can do the term of the increment mass. Okay, so if we know the average of the specific humidity and average of the air density times the area and data set, we can estimate the mass of the precipitable water. Okay. The next example show how to apply this equation. We assume that the saturated air mass is 10 km above 1 square meter, and the surface pressure is 101.3 kilopascal. The air temperature is 30 degrees, and alpha Laplace is 6.5. Okay, so in this case we can start from the z equal to 0, estimate and and what Z equal to 2000 meter. Okay, we can estimate the temperature at the Z2 is about 16 degrees Celsius or 290 degree Kelvin. Okay, we use the forecast constant, we use the same. Okay, and we can next we estimate the power G divided by alpha RA. So we can get the power number is about 5.26, and we can estimate the pressure at the Z2 is equal to 80.4 kilopascal. Okay, we do this for the Z equal to 0, we can estimate the density of the air is about 1.16, and at Z equal to 2 kilometer, the density is about 0.97, and we take the average of the density, got 1.07. And the next we estimate the saturated vapor pressure using the air temperature. We got the 4.4 kilopascal at the Z0. At the Z2 kilometer, the temperature is 17, so we can estimate the saturated vapor pressure is about 1.93 should be ES. Okay. And we can estimate the specific humidity for at the surface is about 0.026. At 2 kilometer, the specific humidity is about 0.015. The average about we got 0.0205, and substitute to equation of the delta MP, or the mass of precipitable mass of water. So we can guess the mass of water is about 43.7. Okay, and we put together in this table. So we just finished from this level to this level, and we can estimate the increment mass about 43.2. We can do further for the 4 kilometer, and we can find the average of the specific humidity and density. So we got the increment mass about 20. So we do until we finish to 10 kilometer. So we have the mass is about 77 kilometer. If we want to check the percent of the total mass, we can see that at the first layer, 2 kilometer above the surface, the amount of the maximum amount of the precipitable water is 57